Keeper 4.5, Taylor series. Alright, so your Taylor series is your series just like your Maclaurin series, but it's centered at some value. So when the center is 0, it's Maclaurin, but if the center is some other number, then it's a Taylor series. It has the same general format as your Maclaurin series. Again, the only difference is that your center is other than 0. Your center could be like 1 or 5 or 2 or -6 or something like that. But the setup and the way that we find our Taylor series is pretty much the same exact way as we find our Maclaurin. Now, the biggest thing with your Taylor series is you're not using a known series. You're literally building the series every single time, and you're building it at that center or whatever center they specify. So in this case, they want the Taylor series for f of x equals e to the negative x, and they want it about x equals -4. So again, just like when we built our Maclaurin series, we're going to start with some of our derivatives. And so we have the first original function at -4 is e to the 4th. Then the first derivative at -4 is negative e to the 4th. The second derivative at -4 is e to the 4th, and so on. Remember, I usually go out to about 3 or 4 or 5 of my derivatives. I just go enough until I can start seeing a pattern, or just have enough values to where I can build a nice series to figure out a pattern. So now that I have all my derivatives, I'm going to go ahead and build my series. And again, I'm using that formula for Taylor series, which is, like I said, exactly the same as the Maclaurin formula. The only difference is instead of x, you're going to have x minus your center. And so in this case, I'm going to have e to the 4th, which was my original function at -4, minus e to the 4th, which was my first derivative at -4, x plus 4. This x plus 4 is x minus my center. Alright, then I have e to the 4th x plus 4 squared over 2 factorial minus e to the 4th x plus 4 cubed over 3 factorial, and so on. All the way until I notice the pattern. I have -1 to the n because my signs are alternating. E to the 4th was in every single term. And then I have x plus 4, that's my center, raised to the n over my n factorial. And so then if I want to write this as a summation, I know that e to the negative x equals the sum as n goes from 0 to infinity of -1 to the n, e to the 4th, x plus 4 to the n over n factorial. Example 2, we have ln x, and we want to do about x equals 2. And so again, I'm going to write out a few of my derivatives about x equals 2. So we have the original function at 2 is ln 2. First derivative is 1 over x, and then at 2 it would be 1/2. Then the second derivative would be -1 over 2 squared. Notice that I didn't write 1/4. I want to kind of start seeing patterns here, so I don't want to simplify too much until the end. The third derivative I'm going to write as 2 over 2 cubed, and so on and so forth. Alright, so I'm going to go ahead and stop here at the fourth derivative, but again, you can go as far as you want to go until you start seeing like a little pattern in your derivatives. Alright, so now I want to write out the series using that Taylor series formula. And so I have ln of 2 plus 1/2 x minus 2 to account for my center, minus 1/4 or 1 over 2 squared x minus 2 squared over 2 factorial, plus 1/4 x minus 2 cubed over 3 factorial, and so on. Now, again, when I go to try to figure out what it is in terms of n, I generally write it without it being simplified. So the first thing I notice is that it's alternating signs. Well, really, the first thing I noticed was that this ln of 2 was different than everything else. So I'm kind of ignoring that ln of 2 for now, and I'm starting with this 1/2 x minus 2. And so again, I noticed that it's alternating signs, but I wanted to alternate it so that technically the third one, or really the second one, is the one that is changing signs. So I put the n plus 1 on there. And then in my numerator, I noticed that if you look at your derivatives up top, your numerator is just factorials. So like, so in this one I have like, this would be 0 factorial, this would be 1 factorial, this is 2 factorial, this is 3 factorial. So what I notice is I have factorials on top, but I'm starting with 0 factorial. So I have to do n minus 1 factorial. And then I have x minus 2 as my center to the n. Over my denominator, I have 2, and then I have 2 squared, so 2 here, and then 2 squared, and then 2 cubed, and then 2 to the 4th, so that's 2 to the power n. and then I still have my n factorial when I built out my series. Alright, so now I can simplify this a little bit just to make my life a little bit easier, a little bit nicer. And so when I go to simplify this, I have negative 1 to the n plus 1 over n minus 1 factorial, x minus 2 to the n over 2 to the n times n factorial simplifies out to negative 1 to the n plus 1, x minus 2 to the n, all over 2 to the n times n. In other words, my factorials cancel out everything but n. Also notice that when I wrote out my summation, I had to include the ln of 2 that I was kind of ignoring. I had to include that in the front. And again, I'm including that in the front because it didn't follow the pattern for the rest of my summation. So I kind of set that aside, put it out front, and then wrote the summation for the rest of the series. That's almost like your plus c value had we integrated this to find the answer. Alright, example 3 says find the Taylor series for 1 over x squared about x equals negative 1. So again, I'm going to start by writing out a few of my derivatives at negative 1. Again, when I write out those derivatives, I notice at x equals negative 1, these values simply look like factorials. They look like 1 factorial, 2 factorial, 3 factorial, 4 factorial. Again, you want to get used to noticing factorials. You want to know what they look like so you can see it when you write it out. Alright, so now when I write out my series, I get 1 plus 2x plus 1 plus 6x plus 1 squared over 2 factorial plus 24 over x plus 1 cubed over 3 factorial and so on. When I write out the actual terms in terms of n, I have n plus 1 factorial over x plus 1 to the n over n factorial. So then I want to take that and I want to simplify it. When I simplify it, I'm left with n plus 1 times x plus 1 to the n. Alright, our last example says find the Taylor series for f of x equals x cubed minus 10x squared plus 6 about x equals 3. So just like before, I'm going to write out a few of my derivatives. So the original function, I'm going to get negative 57 when I plug in 3. The first derivative, I'm going to get negative 33 when I plug in 3. Second derivative, I'm going to get negative 2 when I plug in 3. Third derivative, I get 6 when I plug in 3. And then my fourth derivative, I get 0. And one thing I'm noticing here is if I go anywhere past the fourth, like the fifth or the sixth or the seventh derivative and so on, the 100th derivative, I'm going to get 0. So really, my actual series is only going to go up to the third derivative. Alright, so now I want to build my series. So I'm going to have negative 57 minus 33, x minus 3, minus 2, x minus 3 squared over 2 factorial, plus 6, x minus 3 cubed over 3 factorial. Now I am going to try to go ahead and simplify this. And so when I simplify it, I get negative 57 minus 33, x minus 3, minus, and then those 2's are going to cancel, so x minus 3 squared, and then the 6 and the 3 factorial are going to cancel to be x minus 3 cubed. Now I can't do anything else with this because again, this sum does not go off forever. I mean, it stops because every single term is 0, so I don't need to worry about any future terms like x to the n. This would be my series.